also if the follower is too far from the leader, so it's hard for it to return to the leader's route. And also if the total reward for the simulation is too low, so we can see that our follower hasn't particular behavior that mirror our task. Default hyperparameters of the implemented environment is on the slide. Well, as I said before, one of our subgoals was to choose one of the path planning algorithms. We consider 4 algorithms that we could separate in two groups. One is rapidly exploring random tree and its modification. The other one is classical algorithm A star and its modification dynamic A star, D star. Well, we researched these algorithms in terms of path planning time in the implemented environment and also in terms of length of path in average during the 100 emulations. And as you can see from this table, the most efficient algorithm in terms of these two criteria is D-star. As you can see on this image, the D-star path planning algorithm allow us to build a more straightforward path with less deviations and as you could see in our previous table, it builds this path faster. On the next slide, we can see dependency from the dependency of the path searching time and path length of number of obstacles in the environment, because it's it is also a setting that we can vary. So as you can see, Dista can work efficiently even with a higher number of obstacles, and RT didn't allow us to get such good results. So in conclusion, we present the environment that emulates the task of the following the leader and allows us to train reinforcement learning models. Developed emulator has some configurations to vary, so it can allow us to change a reward function with different coefficients. We can change number of obstacles, so we can change number of points in the route and so on. And the implement emulator expands opportunities of investigating reinforcement learning methods in the following the leader task. Further research includes studying the possibility of transferring a reinforcement learning model that trained on this simple environment to the more complex environments like the ones that models in Gazebo simulator. And spoiler, we worked in this way, and we see that it's really possible to transfer the model trained on this simple 2D model into the 3D one with physics simulation. And successful transfer can save computational time during the training the model, because the modeling of the simple environment, well, it's very more efficient in terms of time than modeling in Gazebo. So thank you for the attention, and I'm ready to answer your questions.
Okay. Thank you. There is any question? Okay, thank you, Anton Selvinov, for your talk.
Thank you.
Thank you.
Is there Pavel Alexander present?
Dmitry Ivanov. It's me.
Okay. Okay. Okay.
I don't know why Pavel was indicated as a speaker, but I will. So you can see my presentation, yeah?
Yes, I see.
Mm-hmm. Mm-hmm. So, I will stop video to not affect traffic. Okay, so I'm Dmitry Ivanov. We I will talk about synthesized speech recognition system. So what's the problem? What's the problem? First of all, I would like to say that the problem is very relevant. Synthesized speech is firmly established in our lives. Amazing example is the presidential election in South Korea this year. The team has created a digital avatar of Yoon Suk Yeol, and it took part in presidential race as a candidate. Yes. And so speech synthesis is artificial simulation of human speech using a computer. It's a counterpart of the voice recognition, and it's mainly used to convert textual information into audio information so that a person can naturally interact with digital devices. But a separate direction is the use of speech synthesis to create a clone of a person's voice. Deepfake voice technology, also called voice cloning or synthetic voice, has advanced to the point where it can faithfully reproduce the human voice with great accuracy in tone and likeness. So attackers can use it to fool voice authentication systems or create fake audio recordings to defame public figures, or combine this voice clone with social engineering techniques to convince people to send money and so on. And voice fake algorithms are constantly being improved. So there is no universal method for determining a synthesized voice. The accuracy of current existing recognition system is also not optimal and significantly depends on the training data set. Given the above facts, the recognition of synthesized speech still remains an urgent problem of information security. So how to recognize synthesized speech? There are two stages in choice of research methods of voice recognition. The first stage is the analysis of the audio recordings for its further verification. Usually is presented in the form of capsular coefficients, which carry a lot of information about the speaker, describe the shape of the vocal tract. There are many different methods for calculating various coefficients. As a result of the analysis of related works, we decided to choose not one coefficient, but to use two coefficients to improve accuracy. LFCC, linear frequency capsular coefficients, and CQCC, constant Q capsular coefficients. The second stage is the choice of neural network architecture. The performed analysis showed that the bidirectional network of long-term, short-term memory is the most acceptable. It's an extension of the traditional LSTM neural network. And there were not so many attempts to train the model using this neural network. Also, this model was not trained using the proposed mixture of coefficients, LFCC and CQCC. The flowchart of program algorithm is shown here. The system receives an input signal in the form of a raw WAV audio file. The file is cleared of empty fragments, after which the spectral features of LFCC and CQCC are extracted in parallel. Then it is necessary to classify the objects and conclude whether the voice is synthesized or not. To do this, we first use GMM-based clustering, and then classify groups of clusters using the bidirectional LSTM network. This approach was chosen because, unlike the classification of individual objects, the classification of cluster groups determines abstract and more valuable hidden knowledge, ignoring noise. Bidirectional LSTM is used for classification. This architecture allows you to analyze not only the previous frames of the input sequence, but also subsequent ones, and determine whether the sound is real, already having a complete picture. That the architecture of the network in common is shown here. But to perform such system, it's necessary to obtain a synthesized human voice, which will be used for subsequent training of the neural network. Based on this, there is a need for a data set that uses various synthesis algorithms. Therefore, in this work, the existing open voice cloning libraries were analyzed, and the 5 most effective ones were selected that have an open source code. So in that table, the table shows the selected libraries which we have used. To test the performance of the synthesized voice recognition, we assembled a data set in English. Now it's in English only. And the existing Mozilla Common Voice data set was taken as a basis. It contains more than 2,000 hours of verified voice. It's in MP3 format, but we converted them. And basic requirements for such data set is present here, you can see. And the last link is a link to a data set which we constructed for this neural network. So the main results of the work is the mixture of coefficients, LFCC and CQCC. For user model, we use GMM model. The architecture is bidirectional LSTM neural network. So we used all of these cloning libraries, and you can test our data set if you research in this field. So thank you for your attention, and please listen carefully to the voice of the person you are talking to on the phone. And if you have any questions, please ask me.
Okay, thank you. Is there any question?
So I will stop share.
Is no a question for the audience? Okay, I have a question. Do you compare your system with the related work in the literature?
Yes, we tested analogies. The problem is that data sets which are used for any other systems are not opened, so you cannot repeat the research such as it is described in some papers. So we created, especially for this work, our own data set. We are going to add Russian language because we think that the language, the result is very dependent on the language on which neural network is training. So yes, the answer is yes.
Oh, I see. Thank you.
Thank you.
Okay. The next talk is the AGI as a means of getting truly new knowledge using existing experience by Vladimir Smolin.
Yes, do you hear me? Do you hear me, guys? Can I start speaking? I don't understand. Do you hear me?
Yes, we hear you.
Yes.
Okay, fine.
Yeah, listen to you.
So my report isn't about some applied task. It's just about directions of development of artificial general intelligence and some ideas about using knowledge for this development. Just we will speak about what is knowledge, why we need decomposition to get new knowledge, and why this knowledge should be hierarchically organized. Okay, and I think with using these tools, we will be much closer to building artificial general intelligence. You know that deep learning is now the main technology for intelligence and have a great successes, and the godfathers of deep learning got Turing reward, and still they are saying that there are some problems with intelligence. So they would like that their nets would learn quicker, would not need so many examples to learn their nets, and some other questions, but we'll mainly discuss this one. Can we try to learn faster? Just the main idea, I think, that if some sets are composed from subsets, and we can make a decomposition of these sets to these subsets, then we can make the model of the composition based on the models of subsets. So if the compositions of the elements of sets have trillions of elements, each subset, for example, can have only millions elements, and it is more than 500,000 quicker to learn these base elements than to study all the compositions. And moreover, if just some of elements of the composition cannot be viewed we can't observe some elements without alone, without other elements. If we know these other elements, we can substitute these new elements from the composition and to study them alone. And it will also help us to reduce the volume we should need to study. So it's one of the main ideas, and I try to show it by some maybe stars of the text. There will be few such places, but this is what I would like to pay attention. The next thing is that neurons don't work with just formal neurons. Neurons don't work with symbols, words, and some discrete concepts. They just make analog transformation. So of course you know that real neurons are firing, but still we are thinking that the main parameter of neuron is activity, so the frequency of firing. And all the mainstream deep learning models also works with formal neurons that are not firing. And they just models of some activity, some analog machine. Also, we are speaking about concepts, some ideas. I'm telling you my ideas in words, but in my neurons and in your neurons, also here is some analog machine that transforms the input information and activity of the neurons. And also this analog activity can be described by digits. Still, there is the most interesting thing is how we are getting these new concepts from continuous information coming to us. And if we understand this, it will help us to come closer to building artificial general intelligence. And this is the way not only to, so we not only should work with symbols and digits, but also we should make high-level models of the environment that should also be continuous and with the same methods, because our neural nets are the same in our brain. We maybe would be able to outline some high-level concepts or some high-level ideas. And so when we are working with concepts and models made by men, we are making secondary intellectual actions. So you or somebody else got some concepts, outlined some objects, and our nets are working with these secondary actions. But the main to go further in cognition is to outline from continuous environment some concepts, objects, ideas, and so on. And just when we are trying to explain some idea-related some idea-related terms, if we use only secondary intellectual actions to explain them, we have a lot of problems. But I hope that if we use first-order primary intellectual actions to explain them, it is much more easier. And I hope if I'll have time just to explain some of them. So just let's try to explain what is knowledge. So knowledge data is all some information, but when some devices or subjects make transformation, they use knowledge. So if just type recorder after reproduced some type, it's using the information which is may be concerned like knowledge, and make some output. All other devices also have some ways to use the knowledge they have in them, inside them, to make the transformation of input data to output data. And intelligence devices can not only use this knowledge, but they also can enlarge this knowledge or make it smarter and so on. There are discrete and continuous types of knowledge, but they can be changed into others. So if we have discrete knowledge, we can show it in continuous way and vice versa. But the main is not to make these ways of knowledge opposite, just to find the way how we can from continuous world get out some discrete concepts. The next, what is I would like to outline, and just it's outlined by some star, is that now we are talking in symbols, words, so we can talk about cat as a symbol, but modern networks, they use vectors to describe objects, sounds, words, and so on. But what should be next? The next should be just the models of subsets that should be neural networks maps. So this when we are looking, for example, for the cat in different states, the vector will be different, but it will never be tree or some tank on the sun. Always the cat will be from different points of view. So this subset will be restricted, and just this subset can represent the description of cat. And also this subset can be described by neural network map, and just we should drop a lot of neurons on this subset space, and when the vector is input vector is inside this subspace, so some neurons that are close to the common, the point just moved, it should be on the curve. The nearest neurons to the vector should be activated. These neurons are nearest from the point of view that they have their close to the input vector of its weights, input weights, and so this can model the state of the input signal by the activation of this neural map. Also, this neural map can reproduce the output vector by the same way as approximation, and moreover, it can display the model of the input vector that is coming from outer world. So this model is universal because if we have sensors, their vector of their activity can be showed by the point of this end. It's in the time it moves directly, and if we exclude the time, it will go without some subset, and the more points we have of this vector, we can make the better model of this subset. And what I would like to outline with this star is that the lower space of the subset and the higher space of the sensors, the higher dimension of the sensor space, the less intersection will be among subsets. So, for example, if we have two flat two surfaces in two-dimensional space, the intersection of the surfaces will be also surface. If two surfaces have intersection in a three-dimensional space, that will be a line, their intersection. And if the dimension will be 4, the two surfaces will intersect in a point. And the dimension more than 4 surface interaction will be very unlikely. And this property is very important. It allows complex sense to be decomposed into simple, independent, low-dimensional components that are amenable to statistical analysis. And the complex sense are not available for statistical analysis because each day of our life are different. And why do we think that these subspaces will be low-dimensional? Just for two reasons: that simple objects have not so many parameters, and the second reason is domain. We are unable to map high space dimensions, so we should decompose complex object into rather simple objects. Just the next central idea I would like to outline is that to make decomposition, we should try to make the model of the input signal. So just these components of so just the neural layer, which is making maps, should be not only for one map and not for 2 or 3. It should be for many maps, and just when we are looking for some complex scene, we can outline from this scene some simple objects and to reproduce their vectors and to make the sum and to compare what was composed to the real sensor signal. And that's is important, but more important that we can divide, we can follow this formula, so we can sum all the other components which are not with index I, and so we can put to this for mapping only this component of complex signal. So we putting the input signal not for mapping on all the maps, but for each map we are putting different signals which are formed due to getting some parts of this complex signal. And this process comes stable when we find really parts which follow this corresponds to the scene we are trying to decompose. There are different definitions of AGI, artificial general intelligence, but they're more popular are rather naive definitions. So that AGI, artificial general intelligence, is a system with limited resources, which can solve any problems in complex environment. It's just technically impossible because only fabulous gene or some other magic things can do everything. Any technical device can't do everything. And comparing this artificial general intelligence with man is also not constructive because we don't know what are real possibilities of man and what and the schedule of tasks the man can solve all this changing. So we're trying to get our definition that artificial general intelligence is the ability to form truly new goals, to acquire acquiring truly new knowledge. So just finding new properties and outlining from the outer world new objects is getting new knowledge. So this understanding that we are making a continuous model of, so the models of continuous space around us, of these components, will make some cognition. And what is, I should like to outline that modern neural networks, they all have intuition. So when it's we gave them some input signal, it transforms to output signal, and it's worked very well. So it doesn't need much time to make an answer. And so it's commonplace, it's called just intuition. But this isn't always perfect result. So just, you know, AlphaZero makes some analysis of variance of different ways of continuing the game and find the best way. And this makes the other way that using not only intuition, but some other ideas. It's like thinking. Just the other term is understanding. So if we make a decomposition of some picture of its components, we're not only sure that we understand this picture, but if we look on this picture from different ways, and still the structure of our decomposition remains the same, then we think that we understand what is we are seeing. Thinking is based on the idea that on one level we can't map all the world, so we should have multi-level structure. So just not to find only simple objects, but some ways of what are the directions of the objects, and the interactions of interactions and the object, and so on. And the main is that when the tasks are simple, the lower levels can fulfill the transformation input signal to output signal and everything okay. And this time the higher levels can use the maps, the model of the complex world to generate the new goals for the lower levels, while this simple goals are fulfilled without the changing goals.
So you have 2 minutes left.
Okay, just I have 2 slides. Consciousness is also not the our soul. So just we have some narrow structure which makes some function. It's not memory, it's not transformation of, but there are 2 main regimes that work. So we can make some deals by intuition, or we can think about it. And this problem, what to do to go on thinking or to start doing, is one of the main problems for us to make our deals. And so this problem to switch these regimes is one. So this the function with which can be realized in artificial general intelligence. It looks for every time controls our behavior, and that's what we would like to call consciousness. And also it should be said that not only conscious is, so not only thinking and intuition is only regimes. So there are a lot of other regimes, and in animals, if they are controlled by their hormonal influence, but in neural networks, it can be controlled by coefficients in training formulas and activation of neurons. And just a few words that not all animals' properties can be developed to the human level, so only human can be intelligent. So it's just for the civilization history that we have language, science, and we can be sapient or from the birth, but to become intelligent, we should live in civilization and to have a good education. Okay, and the last is that truly new knowledge is the knowledge that we can't get from the rule-based knowledge and some new data. So it's just the knowledge that we can get from raw observation, and just examples is some electrical and quantum properties discoveries and so on. So just this mapping and decomposition ideas, just for our point of view, is the way for solving this problem and development of these ideas, where hope can make us much more closer to the idea of realizing artificial general intelligence. Thank you for your attention. If any time to questions, I would answer. If no, thank you for attention.
Okay, so does anyone have any questions?
Very interesting presentation. Thank you.
Thank you. Thank you. Okay, so I'm closing my presentation.
Okay, so thank you very much. We will then go to the talk, a prototype system for supporting a network of information graphs with the ability to assess the nature of the subject's knowledge, by Larissa Ismailova. Larissa, are you ready to share your screen?
I don't see Larissa.
No. Does anyone else from the talk is present? I don't think anyone is, right? Well, neither from a member from the talk seems to be present. So if everyone's okay, we can proceed with the next talk. And if they come, they can present later. The next talk would be multi-level organizational learning in a project-based organization, computational analysis based on a third order adaptive network order. The speaker is Gulay Kambaloglu. I'm sorry if I said it wrong. So are they ready to share? It seems like Goulet is not present, but I see Jan Treur present.
Yes, I'm there. But Gulay should be present, but she probably is not in the right room. I will get a message to her.
Okay, so we can give her a couple of minutes.
Right.
Seems like Goulet is presenting in the other room. So she must have mistaken the link. But we can proceed and sort this out as we go. So let me just see if Larissa is here. If not, then we can proceed with the next presentation. Okay, Goulet seems to have entered this room.
Hello.
Hello.
I'm so sorry for the confusing. I will
It's
share
okay.
my screen.
Perfect. So you will have 15 minutes to show us your presentation, and that will be followed by 5 minutes of questions from the audience.
Okay.
So whenever you're ready, you can begin sharing.
Okay. I'm sharing. Okay. Hello. Can you hear?
No.
Yes, I can hear you and we can see.
That I will follow today.
The sound is not coming.
Okay, I will try again. Sorry. I think it should be work now. I will talk about multi-level organizational learning and the levels of this multi-levelity. And we will see our project-based context, the organizational scenario, and we'll see the model design and the simulation results. Let me first begin with the models of our perception of the world, our mental models. We conceptually have them in our brains, and they make us to understand what's going in the outer reality. As an abstract formalization, these mental models consist of 3 main layers. A subnetwork in the base is for the use of mental models, which is the fundamental step of mental models. Then adaptation layer comes to make this mental model adaptive, meaningly to make us able to learn and also forget. As you know, for us, forgetting is as beneficial as learning, for example, for terminated relationships. And exactly at this point, we need to control this adaptation. So we need a third layer for our mental models. This one arranges the speed and persistence of the adaptation process below. That's all to know about mental models. What about self-modeling network structure? Self-modeling network structure is the representation of the levels of mental models. We also have 3 layers representing all levels one by one. Base level, first order submodel level, and the second order submodel level. Base level is like the framework of the mental model of the scenario, the process. First order submodel levels will have connection states. I will explain them in more detail. And second order submodel level is for the control of adaptation, and it will have H and mu states. I will also explain them. But we will use the second order submodel level for the control of connection weights on level below. And we will have an extra meta control level for the speed control. It will also control the phases of our scenario. Yeah, I will explain them in more detail in next slides when we talk about our models. But first, we need to understand what organizational learning is. With a brief and topic-oriented definition, it's the formation of shared mental models of individuals. Organizations consist of people using their mental models to complete personal or professional tasks. It's inevitable to observe a collective learning process in an organization since no person can be isolated from the organization they belong. This shared mental model, this shared learning, sometimes and maybe most of the times, takes place via teams, departments, or small groups of people. And this brings us to the multi-level nature of organizational learning. What is multi-level nature of organizational learning? Let's see. We have levels of organizational learning. We have extracted 6 abstract levels representing learning levels of multi-levelity. We have individual levels, which is the mental model formation of individuals. It's like the learning process of each of the individuals, each distinct individuals. Then feed-forward learning takes place from individuals to their teams by sharing knowledge and learning from each other. It's a form of feed-forward learning because individuals create a shared mental model for their team here. And then feed-forward learning, feed-forward type of learning continues to flow from teams to organization. Organization tries to adaptively gain the best parts of teams, shared mental models. I mean the best parts of the knowledge the teams have. Here, feedback learning also plays an important role on improvements of teams and individuals. Since this learning back mechanism flows from organization to teams to individuals, individuals improve their knowledge with the help of their organization via their belonging teams. The overall picture of these levels forms the process of organizational learning. This scheme on the left hand displays the overall picture that I just explained. You can see individuals, teams, or sometimes it may be project-based, like in our scenario, and the whole organization here. From individuals to teams and from teams to organizations are the feed-forward type of learning, and the otherwise is the feedback learning. And as you can see in the right, we customized our organizational learning scenario on the axis of risk management. We have Roger as a PMO manager and 2 project managers, A and B, as you can see here, working in the local area. These are the individuals in the local level, as you can see here. And in the middle, there is PMO forum, including Roger and 2 managers from different PMOs, C and D. They will create a shared mental model, of course, by learning from each other for PMO forum in the organizational level. Since this is a dynamic progress, feedback learning also takes place simultaneously with this feed-forward learning process. In the organizational levels, team shared mental models constructed better and bigger shared mental models with the help of shared mental models of teams, with the combination of team shared mental models. And now PMO Central, this one, has a opportunity to draw a global risk management practice with the knowledge gained from teams, bringing information from different local levels, different individuals from local levels. These are the detailed fragments of our scenario. I have explained most of the scenario, but this one is important to see the interpretation of fragments for our self-modeling network design. You can see the interpretations here. These are the feed-forward and feedback mechanisms extracted from the scenario. And we can start explaining our network design. And this is the base level of our design of the scenario. In this base level, we have base level states like individual states of project managers A and B, PMO manager Roger, other PMO managers from different local levels C and D, our PMO forum base levels, and our PMO organization base levels. These base levels represent the knowledge level of individuals on different tasks. For example, for person A, for manager A has knowledge on A1, B1, A2, B2 tasks, but B has knowledge on A2, B2, A3, B3 tasks. Their knowledge areas are both coinciding and also differs. Then let me change the slides. And this is our first order self-model level. It's for adaptation of connections, and it has W states representing the weights of connections below in the base levels. It was for use of mental models, and it's for the adaptation of mental models, and then it will come the third layer for the control of adaptation. This adaptation, these W states works like these connections, intra-level connections. You can see we have, for example, for each individual, we have 4 different connections, and that's why we have 4 different W states here representing all the connections. And we have W states for all individuals and also shared mental models. And also we have these connections. These are the W to W connections. These connections provides the adaptivity of our mental models, that actually individuals and shared mental models. As you can see, from individuals to Roger, and from Roger and the other project managers to organization, we have many arrows. These arrows connects the people, individuals to teams and teams to organization. And we have also otherwise arrows, the opposite arrows, because we need feedback learning to improve individuals by the help of their teams, and to improve teams by the help of their organization. These arrows are for the feedback learning mechanisms. And we have the second order submodel levels, the control of adaptation. These higher order double states represents the connection weights of these W2W connections. Because we have connections between these double states, we need to control them with these higher order double states. And these will also have intra-level arrows like this to control the connections. And also we have the meta control level to activate the phases, because we have 3 phases: individual level, the local level, PMO forum level, and the PMO organization levels. That's why to activate these phases and to control the speed of the learning processes, we need H states here in the meta control levels. And this is our overall model. It's a bit complex, but not complicated. We transferred this model to our MATLAB software and, of course, got our simulation results. And it's time to discuss simulation results. It's our MATLAB simulation results output. We have many states. We have a good, colorful simulation results, and I will explain it. In the beginning, individuals gain their knowledge on tasks, because when you encounter a job or a task, you should first develop your mental model to understand and learn the task. This is for that. And after 20 to 40, this area, we can see a recombination example, because here Roger develops an improved mental model combining the best parts of project managers A and B, as I mentioned. And then we can see PMO forums actions from time 80 to 120. It's basically the formation of organization shared mental model from all local managers via their PMO teams. It's the from teams to organization feed-forward learning levels, as I explained. The last part between time 140 and 80 represents the actions of PMO personnel. It's the decision process of the global risk management practice. These are the simulation results, and I explained it. Thank you for listening. If you have any question, don't hesitate to ask.
Thank you very much. So now we will give with questions. So does anybody have any question? Well, there seems to be no further questions. Thank you very much, Gulay.
Thank you for listening.
your understanding.
So now let's just see if the previous speaker is present. If not, then we can proceed with the next one. So I don't see Larissa or anyone else from that talk. So we will proceed with the next talk.
Okay, so let's continue. The next paper is Semantic Web Technologies, Issues and Possible Ways of Development by Belezerov or Klimov. Are you ready to share your screen?
Well, I'm here. I'm Belezerov Alexander. Wait a second, please. Can you hear me well?
We can hear you.
Oh, well. Okay. Sure. Well, and what will my talk be about? This state-of-the-art research is about to outline the current state of semantic technologies and their possible development path. A significant part of the content of the World Wide Web is intended for human reading and not for program processing, especially intelligent processing. In theory, semantic technologies should give structure to the content of the World Wide Web so that the search engines will work at the level of data and not at the level of web pages. This requires a universal method of machine-readable description of data. And it should be the semantic web. That's how it looked in Forgotten Dreams. And it is a public global semantic network that standardizes the presentation of information in a form suitable for machine processing and is formed on the basis of the World Wide Web. It should, but it didn't at the moment. Tim Berners-Lee, the inventor of the worldwide of the semantic web, proposed the name semantic web and called it the next step in the development of the World Wide Web, and further proposed the term giant global graph. And how is it started? From this model. Original semantic web should work in parallel with the World Wide Web using the HTTP protocol and URI resource identifiers. But there is a hole in this web. Addresses in the global network as the main method of identifying entities are short-lived and non-permanent. And also there is no single standard of generating addresses, but there are only syntax agreements. And it should be recognized that the main reason for the extremely slow development of the semantic web project isn't this hole, but an assumption that site owners will build a semantic web over the World Wide Web on their own. Of course, they will not. In recent times, semantic technologies kind of stagnate, but positive shifts in the semantization of the web are beginning to occur. However, they didn't come from where they were expected. The one is folksonomy, the classification implemented on a voluntary basis, the practice of joint categorization of information such as texts, links, photos, video clips, etc., by means of arbitrarily chosen text. And the second one are simple APIs of popular services and microformats, HTML and XHTML text, endowed with an alternative meaning through their parameters. This small brick from the same small illustration of this presentation will allow to build not a semantic web, but a hybrid web that consists of web pages with metadata. Moving on, about the problems. Everything is simple here. On the left, we have expectations, and on the right, reality. So, first of all, it's permissible to call a knowledge graph a semantic storage containing the most complete description of a certain subject area. But at the same time, it contains only and only a large structured set of facts, related facts, but not knowledge. Second, compared to relational tables, there is no special additional data linkage in the graph. Transferring data from one schema to another doesn't increase the number of links and doesn't add new linked data. And also, with the help of the logical conclusions, it can obtain new statements, but not knowledge. So, as we think, we should not try to make a strong AI from a weak that is capable of looking for text meaning, and we should do something for the only intelligent interpreter in our search system now, the user. We should do something at the first with his user interface and with the metaphor of a search box. The search box is familiar to everyone who has ever searched for something on the web, but in a semantic search system, it leads to incorrect user behavior. Instead of using the full power of natural language query interpretation mechanism, it will compose queries simple and atomic as much as possible, as traditional search engines interfaces taught them. And maybe the graph model would be more applicable. However, this isn't the reason to abandon AI in semantic search and semantic technologies. Modern technology has reached a sufficient level to spread voice input interfaces everywhere in the form of voice assistants. So the future of semantic technologies may be in a natural language processing. Voice assistants rely on a technology called natural language processing, NLP, which uses artificial intelligence and machine learning. And this means that over time, they can learn the speech patterns of the person speaking to them, as well as their ways of expressing emotions, preferences, and other behaviors. Perhaps this will bring real meaningfulness to the semantic search implemented on the basis of neural networks. So, in conclusion, the aim of semantic technologies nowadays is only to standardize the collection and processing of data, automate data exchange between independent applications, and refine data search. What is not the aim is to work with meaning. No. The next step in the semantization of the web could be speech and emotion recognition technologies, as well as the further development of neural network language models. Another one step, using microformats, markup languages familiar to web developers, and enhancing user interfaces. No need to come up with another standard for the web. You need to expand the most successful ones available, microformats based on HTML and XHTML. You shouldn't rely on the altruism or ideology of millions of people that they will take and relearn. No, microformats either way. So thank you, really thanks for your attention. If you have any questions, I will try to get them.
Okay, thank you for your presentation. Any questions for the audience? Okay, it appears not to be any question left, so we will continue with the next article.
Thank you. Thank you all.
So our next paper is The Concept of Intelligent Data Lake Management System, Machine Consciousness, and Universal Data Model by Anna Senger.
Yes, I'm here. I'm ready. I'm so sorry, I have low connection of internet, so I can't turn on my camera, so I'm sorry about it. So I will turn on my presentation. Okay, so hello everyone. My name is Anna Zanger, and our topic for today is about the concept of an intelligent data lake management system. I will talk about machine consciousness and universal data model. First, I want to review problems of current data lakes systems. The evolution of technologies and the ever deeper integration of automation tools lead to constant increase in the amount of data processed by enterprises. To work efficiently with large volumes of disparate data, the concept of data lake began to be used. Data lake can be defined as a vast repository of raw data from various sources that can be transformed and analyzed. With the exponential growth of amount of data stored in the data lake and the lack of control over the loading and the organization of data, the problems of potentially important data being unused is often common. So, based on the recent research, the following problems have been identified. There is no universal concept of data lake. Research gaps need to be filled in data lake architecture and data lake management. And the absence of a comprehensive design and implementation strategy that considers interdependencies between aspects of data lake is a major challenge for using data lake in practice. The existing problems are related to the poor development of the theory of data lakes. We propose the concept of data lake, which will overcome many existing problems. So at first part of my presentation, I will focus on consciousness and subconsciousness in data lake management system. First, we will talk about artificial consciousness. Biological evolution has shown that the consciousness is powerful and flexible and creative control system. Data lake may well be an object controlled by consciousness. It is developing, moves in time. Consciousness should be built in the data lake management system and manage only a specific data lake. In the process of management based on available resources, the consciousness provides the ability of receive new data from storage, optimize the query execution time, response to equipment failures, interact with a team of administrators who manage data lake, and set parameters for functioning of the data lake. The data lake control system will be consciousness if it meets the following requirements. Self-knowledge. The system has a completely knowledge of its current cognitive state and the data produced by all its sources. Self-control. System is fully aware of performance and status of its sources and data manipulation tools over time. Self-awareness and self-reflection. System is aware of the internal and external changes that it causes. Self-information. The system globally communicates its cognitive state to all models of the system whenever state change occurs. To solve the problem of data lake management, consciousness will have a service knowledge base contains following knowledge about all services on which data lake is located, all logical data objects stored in data lake, all sources of data, all available places where you can look for missing data, all data transformations performed in data lake, all users about all their requests, about history and data lake KPI values, and about data lake administrator. the subconsciousness mind has a larger memory than the consciousness mind, and the several independent intelligent agents functioning in parallel. In contrast, the consciousness mind having a single agent. Consciousness is engaged in comprehension and logical conclusion based on the information received. Consciousness develops new models of behavior and problem solving in unknown situations. Subconsciousness agents perform various auxiliary actions and pull memory blocks into consciousness that may be associated with solving current problems. Subconsciousness quickly works based on ready-made models. Intuition is used to transfer information from subconsciousness to consciousness. Another mechanism to transmit information to consciousness is emotions, which shows the consciousness what is happening in subconsciousness level. If it is advisable to use subconsciousness of data lake for following regular actions: replenishment of data lake with new data, checking service health status, evaluation of stored data objects and their collections, evaluation of incoming requests and their execution time, clearing memory for non-frequently used auxiliary data and indexes fetches, optimization of placement of data and their aggregates in storage, and creation of service data selections and indexes to speed up query execution. To predict data lake performance in the near future, the subconsciousness uses AutoML library. All calculated values of indicators and trends become available to the consciousness, which takes actions to avoid critical situations and provide service level agreement. To efficiently manage the data lake and automated support, an intelligent adaptive data lake management system is proposed, which has following features: the presence of consciousness to manage parameters of data lake, usage universal data model that includes metagraphs, tables, multidimensional cubes. I will talk about later. Support for family of languages for working with metagraphs, including declarative and navigational queries and data manipulation languages. The presence of some subconsciousness mind to perform frequently repeated procedures, the presence of agents looking for information missing in data lake in external sources, bots that provide interaction with administrator and customers in natural language, AutoML system used by subconsciousness to predict characteristics of data lake, and library of classical mathematical algorithms for working with graphs adapted for working with metagraphs. So on the second part of my presentation, I will tell you about universal data model. To structure a large amount of data, it is necessary to use data model that provides an unlimited number of data nesting levels and nesting encapsulations. These features will allow operating with data at the upper generalized levels and access to details only when the needs arise. Metagraphs are only one type of data model that has this capability. Several more element classes must be added to the model to work with any data structures. Tables, multidimensional cups, virtual tables, and virtual multidimensional cups. To work with tables, you need several auxiliary objects: table row, table column, and key. And to work with multidimensional cubes, you need auxiliary elements, dimension, hierarchy of dimensions, and indicators. So let's talk about Metagraph model. Metagraph is kind of complex network model proposed by Basu and Blenning in their monography, and then adapted by authors for information system description. In Basu and Blenning model, the metagraph is defined by expressions that you see on the slide. X is a generating set of metagraph set of elements, and E is set of edges. The concept of metavertex isn't presented in this model. This version of Metagraph model is more suitable to describing direct processes than for describing process graph data structures. So we will talk about annotated metagraph model that extends the idea of original model of Bayesian planning. Metagraph model may be described by a set of metagraph vertex, set of metagraph metavertex, and set of metagraph edges. Metagraph vertex is described by a set of attributes, and metagraph edge is described by attributes, source and destination vertex, and edge direction flag. The metagraph fragment is described by an element that belongs to the union of vertex, metavertex, and edges. Metavertex, in addition to the attribute, includes fragment of the metagraph. The presence of private attributes and connections for metavertex is a distinguishing feature of metagraph. Metavertex may include a number of low-level elements and may be included in a number of high-level elements. So metavertex with its private attributes and connections become a whole that cannot be separated into its components part. On the next slide, we see example of annotated metagraph. On the picture, we see 3 metavertex, 5 vertex that are connected with several edges that connect metavertex and vertex, metavertex to each other, and different types of connection. Metagraph model allows describing a complex data structure, and it is metavertex that allows implementing emergence principle in data structure. Let's talk about another type of graph data model, protograph model. Protograph can be thought as a graph without edges. The role of edge is performed by the junction of the vertex to each other. So protograph is given by the set of elements and neighborhoods matrix consisting 0 and 1, when 1 means the neighborhood of element A to element B. Ordinary graphs are protographs in which elements are divided into 2 element classes, and the rule is that elements of the same classes cannot be adjacent. On the pictures, we see 2 types of protograph model, undirected protograph and direct protograph. Archigraph with number n is protograph with the division of elements into n classes and corresponding division rule. The number of classes into which elements are divided is the most important characteristic of the archigraph. So on this picture, we see metagraph of Bayesian blading that is shown as archigraph model. So annotated metagraphs are archigraphs with 5 classes of elements: vertex, metavertex, edges, meta-edges, and attributes. So some of adjacency rules of elements of different classes in the universal data model are presented on the slide. Each edge can be adjacent to one of the elements of the following classes: vertex, metavertex, tables, virtual tables, multidimensional cubes, virtual multidimensional cubes. Same class elements is for meta-edges, and metavertex and meta-edges can contain with themselves vertex, metavertex, edges, meta-edges, tables, virtual tables, multidimensional cubes, and virtual multidimensional cubes. The proposed universal data model will allow building complex metagraph structures and link tables and multidimensional cubes to them. This will make it possible to work on a single data structure for all types of applications. On the next part of my presentation, I will tell a little about geographic metaphor of data lake. First metaphor is a single data lake. The example of it is Sivan Lake. This is a simple single data lake with that have agents in control system and works only in this data lake. Second geographic metaphor is interconnected data lakes. For example, Great Lakes in Canada and USA. So this metaphor shows us data lakes that have open parts of their data structures to each other and exchange data with each other. Very large data lake, data sea, our next metaphor, for example, Caspian Sea. So there we are talking about existing data lakes begin to open more and more to each other and open all data. Then then they merge into one big sea of data, and all the metadata of different consciousness are combined, and whole structure begins to be controlled by a single big consciousness. The next is data sea with a small open part of data. For example, Baltic Sea or Mediterranean Sea. On the slide, we see a picture of Baltic Sea. Most of seas on the Earth are connected to the world ocean, and but these connections are different from each other. And by analogy, public access of data to the data of the data lake via the internet can be organized in different ways. I'm sorry. There is seas that are connected to the world ocean through a narrow strait, such our examples. And this is a direct analogy to a large data lake, which has small open part to the internal data structure or to the data lake, to the internet, I'm sorry. And next metaphor is data sea with numerous exposed pieces of the internet data accessible via the internet. So there is category of seas that are covered from ocean by right of islands. This is analogy of two large data lakes, which have numerous exposed pieces to of the internal data structures that are available via the internet. And the last metaphor, geographic metaphor, is data sea wide open to the internet. For example, Norwegian Sea. So this is the last category of seas, seas that are wide open to the world ocean. This is an analogy of with a large data lake, the entire internal data structure of which is open to access from the internet. So on the last part of presentation, we will talk about conformity with the development of ERP for current data lakes. In 2010, in parallel with first proposal of data lake concept, first independent proposals of the ERP3 concept appeared, reflecting various aspects of the future class of systems. And in 2013, transition to ERP3 was made, associated with the rejection of monolithic application and transition to set of integrated cloud and local applications that solve all the necessary tasks of enterprise management tasks. These applications are different DBMS and data stores, which may use different data models. Data of such corporate system can be successfully placed in a multi-paradigm data lake, but ERP3 system were described and developed in 2013-2015, and the necessary data lake in 2019-2021. In conformity with the amount of data for current data lakes. So this is the second aspect in which the existing concept data lake lacks from the development of enterprises applications is the need to copy all data of transactional systems to the data lake. To reduce data duplication and copy operations, embedded analytics has been actively developed since 2014. This is facilitated by the fact that ERP3 applications mainly use big data platforms and as technological platform. Building analytics works directly with transactional data. It doesn't solve all problems, but it significantly reduces the need to use data warehouses and data lake. Connecting a large number of edge devices increases the amount of stored data up to exabytes. Such volumes naturally exclude the possibility of duplicating all data for use for analytics. And at the end of presentation, I want to tell you about prospects of data lakes. Development of proposed concept should not cause any extra problems, and development of experimental system may require only 1.5 or 2 years. The creation of such system and the beginning of widespread use of implemented principles will make it possible to eliminate the gap of data lake concept from the architecture of corporate management systems of large companies. The concept of data lake management system allows to manage all data of large company use both in OLAP or OLTP modes with high degree of autonomy and without involving many employees. The data lake management system will independently decide where and what to place and what data needs to be cached. This approach, in our opinion, will solve the existing problems. So thank you for your attention. If you have any questions, I'm happy to answer them.
For the presentation. Any question for the audience? Okay, it appears not to be question. Thank you, Anna.
Thank you very much.
So let's continue with the next presentation. It's elements of semantic analysis based of lambda calculus by BICA Wolfenhagen. He present? It appears not to be present, and I believe they are the same people that are missing the last presentation. Larisa Ismailova or Sergei Kosikov. Are you present? Okay, so it appears they are not present. So I believe we are going to take a break, half-hour break. So if you want to move to the auditory to see other presentation, you're welcome to do so. And we resume activities in half an hour. Thank you all.
was present? No, right? And a singer or singer? No estaba.
Hi, can you see me?
Yes, hi.
Hi everyone. We will start with the presentation of Lars Russ.
Yes.
Yeah, okay. Jan Troll, Violeta Kucharska, and Anna Viviora with the presentation with title Adaptive Dynamical Systems Modeling and Transformational Organizational Change with focus on organizational culture and organizational learning.
Exactly.
Please, Lars, go, please, with your presentation. Thank you.
Welcome everyone to my presentation from the paper that me, Lars Russ, Jan Troja, Violeta Kucharska, and Anna Viabara wrote together. It's about, like already I said, computational modeling of transformational organizational change with a focus on organizational culture and learning in a hospital-related safety culture context. To introduce the topic, it becomes more and more apparent that there's an urgency to adapt our systems and organizational structures to the changing circumstances and learn how to facilitate sustained change. Organizational culture is a priority nowadays, especially after COVID-19 put further pressure on our public healthcare systems. The concept of healthcare safety culture is closely related to constant learning culture, which is composed of components as learning climate and mistakes acceptance as a natural part of constant learning. There's two approaches nowadays on how to see organizational change. The classic approach is to see organizational change as an external process that can be applied to any organization, but the more recent, more current approach is the dynamic adaptive systems approach, in which organizations are seen as complex adaptive systems, in which organizational processes are dependent on the interactions of independent individuals. So in this approach, change isn't seen as something applied to the company, but a change within the systems of the company, in adaptation of an organization towards the new context or environment. And especially in this field, computational modeling and formalization of this organizational change and learning process is still largely unexplored. So we aim to provide an adaptive network model of transformative organizational change and translate a selection of organizational learning and change processes into computationally modeled processes. For that, we conducted a literature review and where we found that there is right now a systems model of organizational change that was proposed by Maas and van Hotkamp that sees organizational change not as a linear process, but as a multidimensional mechanism in which an organization adapts to its influences. Organizational change is hereby significantly influenced by the organizational culture or how the organization deals with new input. The culture of an organization thereby is mainly shaped by its members' shared values, norms, and assumptions about reality. And in this context, a constant learning culture aims to provide an environment for sustained learning possibilities or change possibilities for transformation for the organization on both the personal and the organizational level through mistake acceptance and collaboration-driven organizational culture. Organization could be seen as dynamic adaptive systems on individuals' actions and processes of actions and sense-making. In a systems perspective, these transition processes are merchants of the interplay of various actors pursuing their interests, but the overall direction is usually driven and propagated by actors with a larger plan or visions in the context of organization. This would be leaders or the managers. Transformational change is characterized by the reshaping of strategies and behaviors, as well as a shift of values and culture. And this organizational learning usually takes place by feed-forward learning, in which information processes get propagated towards higher organization levels, and feedback learning, where changes on the organizational or team level get propagated back towards lower levels of the organization. While this whole research is quite far-reaching, we decided to have a research focus in which we try to first confirm if the explored dynamic systems sphere of organizations can be translated into the self-modeling approach that we use for our simulation. But also we want to try to verify if a shift in learning culture happens towards a constant learning culture if we apply those organizational change processes. To be more precise, however, we want to also explore the organizational learning mechanisms effects themselves and their effectiveness in correcting inaccurate mental models, organizational processes, and particularly feedback and feed-forward learning, both in organizational and at team level, learning from mistakes brought forth by Kucharska, and diet learning. As also, we want to see if leadership inspired or instructed organizational cultural change, incentives, for example, workshops, or like the restructuring of organizational structures is valuable or is effective. For this, we will use the adaptive computational network model approach proposed by Jan Troy. And in this, we have a network model, which is mostly defined through its connections that translate between real-world causal relations into a network structure, which weights demonstrates the importance or the strength of the connection, a timing which is done by a speed factor that represents the rate of change of certain values, and aggregation functions that determine how multiple inputs to a node are combined. We reach adaptivity in this model through higher order self-models that usually consist of self-model replication states and enable an adaptivity and reactivity of the weights, the speed factors, and the network characteristics, like the parameters of the combination function. Our model and our simulation surrounds a hospital-related safety culture context in which we model a three-step task as mental representations of all entities in this simulation. We have 4 young doctors that have a representation of this task in their head. We have 2 teams where the shared mental model of this task is saved, and 1 experienced doctor, which also has the mental representation, and 1 organizational mental representation as well. This task could consist of anything from CPR to a more complex, more step process. But for the sake of the simulation, we kept it as a generic 3-step process in which the perfect representation would be task 1 is executed, then task 2, then task 3. But if error can occur, if task 1 gets executed and task 2 gets skipped, and we try to prevent that, we try to save this. For this, we have the base level construct of just the real world cause and the mental representations. The second order describes the weights of the different connections, as well as an error detection mechanism of the real world occurrence of the task. So if we detect an error happening there, it triggers organizational learning mechanisms. Those we see on the second order that influence the first order weights, which then influences the base level and the actual mental representations. Here we have the different mechanisms that we examine. We have feed forward and feedback learning in purple, in which we have in monthly meetings feedback and feed forward towards the organizational level to build a shared mental model on the organization, but also back to learn from this shared mental model. We have the daily shift meetings, in which on a daily basis, the teams meet and the young doctors meet in their teams with the experienced doctor to talk about the recent shift, to talk about the mistakes happening there, where also feedback and feed forward learning happens, but not on an organizational, but only on a team level. We further also have a we also have in yellow the states and the mechanism that detects mistakes, which gets triggered when on the first base level in the real world a task gets performed wrongly, in which first the error gets detected, the young doctor is proactive about it, registers it with them, what then creates the supervision reflection in which he and the experienced doctor talk about the mistake and take the lessons from it in the form of diet learning. And the last thing that we have as a mechanism is in red, which describes the restructuring of organizational structures, which changes some adaptivity parameters within the aggregation functions. The light blue colored nodes are just internal nodes to control the simulation. So they're not really important for understanding. When we run the simulation, we first run the learning by mistakes mechanism. Then we simulate 3 days of daily reflections. After that, we simulate a restructuring of the company or organization, in this case of the hospital context. And then we simulate a monthly meeting, a monthly reflection upon everything. We see already that when learning from mistakes, there's a huge change in the mental representations towards a corrected representation. We see that in yellow, for example, when an error occurs, it triggers the error detection mechanisms, which triggers the young doctor to be proactive about it, which then triggers a cooperation between the experienced doctor and the young doctor, which elevates, for example, the brown lines that you see on the left, on the bottom, which elevates them to a higher point, to nearly 1, towards the correct representation, towards the correct understanding of after task 1, task 2 follows. You also see that the wrong connection that was at point 0.9 in the beginning already goes lower to 0.3, which represents the shortcut that some doctors will take from task 1 to task 3. So already here we see a correction of the mental representations, but not a full correction. Then the next time we have daily shift reflections, so a daily reflection upon the mistakes or challenges occurring in the context. And in red highlighted, there's one of them mental representations of the young doctors of the correct task succession. But you see that every time when we trigger the first feed forward part of the daily reflections, in which they only share their knowledge, they only share their mistakes, there's no learning yet, because it builds the team mental model, the mental model on the team level. It creates it only then. Then on the second time, where actually the feedback learning happens and the young doctors' mental representations can be influenced by the team mental models, we actually see that it corrects to a certain degree. We see also, like, over the 3 shifts, the 3 days actually modeled, we see the change actually applying and changing from a quite wrong mental representation towards a correct one. Also, when we see it in more detail, we really do see how the team mental model gets built, the team mental model gets adjusted, and then it influences the young doctors' mental models. We also have the monthly reflection, and here we actually examined how much the change of both of the reflections reflection would be if there was a restructuring in the teams or if there was no restructuring in the teams. When we had a organizational restructuring, we saw that the learning effect was quite effective. We see a huge change. However, when there was no change teams, so when there was no restructuring of the company and the focus of the doctors was less, we see that there's only less of a learning effect. So what can we conclude from this? Overall, the model successfully showed emergent behavior, reflecting the empirical findings in the discussed literature, confirming its validity. We also observed and confirmed for the model that learning from mistakes is one of the most powerful tools for individual learning. The simulations also show that the daily shift reflections have a constant and robust positive impact on the correction of the mental models, suggesting this tool as the most reliable mechanism to choose. The model as well demonstrates that a cultural shift towards a constant learning culture, verifiable by many and interacting learning opportunities, occurred. Lastly, the model and its results further confirm that the self-modeling approach by Jan Dreuer is a suitable approach to formalize the systems model of organizational change brought forth by Maas and van Houtkem, and the proposed dynamic systems view of organizations brought back by Fowler, Hazy, and Silverstein. However, this research obviously also has limitations. It's only simulation, and the simulation is only scenario bound and only reflects some organizational learning mechanisms. A further advanced model should also integrate observational learning for the task observing doctors, or could integrate counterfactual thinking as a learning and decision-making mechanism as proposed by Balvanka and Troyer. Also, a combination with additional computational models in this domain could be added as well to create a more and more holistic representation of organizational transformations. Lastly, the translated mechanisms of this model can be extracted and reused in other related models. Therefore, future research suggests itself in an extension of the proposed model, as well as in the creation of a library of computationally translated transformative organizational change mechanisms. Yes, those are the references, and if there's any questions, I'm happy to answer them.
Okay. Is there any question? No? Okay. Thank you, Lars.
Thank you.
Is present Sushan Chelin? My team is not present right now. So the next talk is present by Antonio Lieto. Is here Antonio Lieto? Okay. I think is now present the two next. So we're waiting 5 minutes in order to contact the next speakers.
Yes, thank you.
Okay, Julian is not here. Can we continue with the next talk? Presented by Antonio Lieto.
Yes.
Okay, can you hear me?
Yes.
Okay.
We can. Okay. Okay. So.
Good, I'll try to
please. We will start with the presentation entitled Degree 2.0, a diversity-seeking, explainable, and effective art recommender of social inclusion by Antonio Lieto. Yes, Antonio, you have 20 minutes, and please, you can now start with your presentation. Thank you.
Okay, so thank you very much for the introduction, and thank you to the organizer of the conference. So today I'm going to talk about a specific application of a common sense reasoning framework that has been developed a couple of years ago, and that has a strong component of cognitive inspiration. The reasoning framework is called the TCL. I will not have time today to enter into the details of this framework, but I will try to give you a hint about how it is used, which kind of problem solves, and how it has been used in the context of affective inclusive recommendation of artistic element within the Degree system. So first of all, the general, let's say, area in which the overall framework is co-located in is the area of, let's say, of the research in common sense knowledge and common sense reasoning, which is one of the, let's say, represent nowadays one of the main, let's say, open areas, unsolved areas in the context of artificial intelligence, even if it is a sort of old problem. And it is important to point out this preliminary work by Marvin Minsky that already pointed out how, let's say, solving the problem of common sense knowledge and common sense reasoning can really mean to deal with and to solve the issues concerning the connection between the perception and high-level reasoning within a unique general agent. And indeed, in the history of artificial intelligence and cognitive modeling, we have had a bunch of different kinds of approaches to solving the problem of common sense reasoning, starting from, let's say, the preliminary heuristic approaches by Newell and Simon, to fuzzy logic, to circumscription, to other types of, let's say, proposals that have been done. Now, let's say an important aspect to take into account when we talk about common sense reasoning is that with this type of expression, we mean all the types of inferences like induction, abduction, default, which are non-deductive, so are non-monotonic, but that also have this ingredient of typicality. And I will try to explain you in a minute why this aspect is important in the context of our framework and then in the context of our application. So in particular, an important aspect that is relevant for the problem of common sense reasoning is how to combine the typicality, okay, with the problem of compositionality, which is an irrevocable trait of human cognition. Why it is difficult to reconcile these two elements? Because we encounter what is traditionally called the pet fish problem. So what we have is that if we have a typical representation, for example, of a concept like what is a pet, and a typical representation of a concept like what is a fish, okay? And then we try to combine these two prototypes, these two typical representations in order to generate a novel concept like the pet fish. Well, we see something strange. we see that the composition of this concept is not merely done by the additive inclusion of the typical features of the two composing concepts, but there are some elements which are inherited from one of the two concepts, some elements which are not inherited. There are new features like the fact of being read that are inferred, okay? So this is a challenging problem to solve for, let's say, artificial system, but it is a crucial problem to solve because the way in which we invent and generate novel knowledge follow, in most of the cases, we as humans, I mean, exactly this type of approach. So the entire common sense reasoning framework that we have developed a couple of years ago with Gianluca Pozzato was aiming at solving this pet fish problem, was aiming at having human-like concept composition, and let's say in this way it was possible to have solved, let's say, the so-called pet fish problem. And we actually showed in a couple of publications how our framework is able to handle with the pet fish problem. So he is able to provide automatically human-like concept combination by combining these three ingredients that you can see here, by combining a description logic of typicality. So by, let's say, having a language, it allows you to tell that there are typical elements of a category which are, for example, also member of another category. Like, for example, one can say that typical students are social media users, okay? It is possible also to add probabilities to this kind of statements. So we can have, let's say, attached the idea that some statements have a probability value, while other statements are rigid. It means that there is no uncertainty in that kind of statements. And in addition, this comes from the second point, the second semantics, which comes from the probabilistic logic programming. And the third point, which is a crucial element of our, let's say, framework, is inherited directly from the field of cognitive semantics, according to which if there are two or more concepts to combine, there is always a head from which we want to inherit more features, and then there are one or more modifiers from which we want to inherit less feature in the final combined concepts. So the details of the logic of the framework are in this paper published a couple of years ago. But in a nutshell, this kind of framework allowed us actually to deal with the knowledge bases equipped with real data, where we had both probabilities associated to typical typicality-based statement, or let's say rigid statement, like in the case of the pet fish. We know that, for example, a fact where there is no uncertainty is that all the fishes live in the water. This kind of, let's say, language was then used to generate all the possible probabilistic scenarios based on the fact that some features of one of the n concepts involved in the combination were inherited or not. The ranking, the probabilistic ranking of these features was provided by the Disponte semantics. And again, here, I don't have time here for going into the technical numerical details. And finally, the scenarios that were selected had to respect the third ingredient of our framework, which is the cognitive heuristics head modifier. So the idea is that when there are conflicting elements, the head has to win. So we want to inherit and we want to retrieve more scenarios, the scenarios giving more importance to the head. There are other caveats, like, for example, the fact that our system, our framework is able to exclude inconsistent scenarios. But again, I mean, there is no really time now for going into the detail. One important point is that we showed how this framework was able to solve the petfish problem and was also able to model other kind of cognitive phenomena like the conjunction fallacy. And in addition to the area of cognitive modeling, it has been used and also in a bunch of other applications like computational creativity. So inventing, for example, new characters for a cartoon, or in the area of a recommender system. In order, this was a project done with RAI, where we combined the classical genres of the website of RAI, which is the domain public broadcasting company in Italy, in order to generate novel hybrid concepts like, I don't know, combining the concept of what is a Western movie with what is a drama. Okay, so combining, having new hybrid concept and reclassifying the entire multimedial catalog of the company in order to recommend also these new, let's say, hybrid, these reclassified items in the hybrid concept created with the TCL logic to new users in navigating actually the multimedia catalog. So today I'm going to talk about an evolution of, let's say, this overall framework. It is not actually an evolution, but it is a novel application of the framework, which extend a previous system, which was called Degari. The way in which our system, which is a system that is able to dynamically generate, let's say, emotional classes and dynamically classify, let's say, elements within this novel emotional category. And as I mentioned, the main novelty with respect to the previous version of the system is that as I will show you, the system is able to suggest, based on this kind of generative capability, not only, for example, items based on the fact that they evoke the same emotion to some particular users, but also, let's say, items based on the fact that they evoke opposite emotion or similar emotion. So there is a more nuanced way of providing this kind of affective labeling, affective classifications. But I will show you in a minute what we have. So how we applied in this framework, in this system, our TCL framework, well, we actually started from the so-called Plutchik theory of emotions, which is a well-known affective theory developed in the context of cognitive psychology. This is an interesting theory of emotion because it fitted very well what our system, what our framework does. So our framework, our common sense reasoning framework, is a framework providing human-like concept combination. And this system, this emotional framework is interesting because it provides a way to generate complex emotion, compound emotion, starting from what are defined within this wheel that you see in the slide, basic emotions. So the idea is that there are some very basic emotions like joy, trust, and so on and so forth. And then there are a bunch of different kind of dyads, which can be primary dyads, secondary dyads, or tertiary dyads, based on the combination of different kinds of emotions. Like, for example, the concept of love, according to this theory, can be obtained by the combination of the concept joy and the concept of trust, and so on and so forth. So we used this schema to generate the prototypes, the human-like, let's say, representation of these compound concepts by using our Degari reasoning engine. Now, the problem that we had here is that once we had generated these elements, it was not actually possible for us so once we, let's say, we started from an ontology developed according to the theory of Plutchik. The point is that once we started with this ontology, we didn't have the features, the typical features associated to every and each element of this class. So we had the class, I don't know, joy, but we didn't know what joy was. So what are the features of joy? And in particular, let's say our framework, let's say, tries to reason on, let's say, probabilistic features. So this was a problem. So what we did was using a very well-known lexicon, affective lexicon, which is called the NRC lexicon, that ranks the words which are, ranks probabilistically the words which are more likely to be associated to, let's say, these emotional concepts. So what we did was to take this lexicon in order to, let's say, populate with the properties, all these empty classes within the ontology. The standard ontology was translated in our TCL framework, which is a non-monotonic, let's say, description logics. And in this way, we were able to use the reasoning engine in order, for example, to obtain from the combination of the concept of joy that was now equipped with these features and the combination of the concept of trust equipped with these features, the final concept, which is love, which does which solve, let's say, in this new context, the pet fish problem. So it inherits more elements, some elements from joy, some elements from trust, according to which is the head and which is the modifier. So in this way, we were able to have a knowledge-based system done, let's say, using our TCL reasoning engine. Now, this TCL reasoning engine is equipped in, let's say, a system named Degari that has been used in this particular case for affective recommendations in museums. Okay, this is an ongoing project that we are carrying out. And actually, let's say, based on this kind of classification, the system is able to, given an input, let's say, a document like this one that can come from the catalog of the museum, or given an input, for example, some responses that the users can provide with respect to a particular artwork by using a mobile app. Okay, the system can assign let's say, an affective label to these items while the people are visiting, for example, the museum, and they can also explain why a certain affective classification has been provided. So it is possible, for example, in the case of the catapult for the system, it is possible to explain why the associated emotion has been O, which is a complex emotion composed by the basic emotion of fear and surprise, and the answer is that, well, the answer is O. The answer of this classification is O because either in the text that you write in the app or in the emoji that you used in the app, we detected these keywords like surprise, tartar, kill, that match with the features, the typical features which are associated to this kind of concept. So in a nutshell, I want to really show you, this was something that, let's say, was already available in the first version of the ontology of the system. What we did, let's say, in this second version, and you can see here a video. You here have, let's say, can see how the TCL, this is the language in which the TCL logic is transformed. But the idea is that once we have a representation either coming from the catalog of a given item, or let's say something that comes from users, once we have this kind of, let's say, JSON representation integrating all the data about a given item, we are able to, let's say, classify according to our, let's say, generated emotion, these items with emotional labels. We are able, as I already mentioned, and as you can see here, to explain why, let's say, a given item has been associated a certain emotional label. And in addition, we can also recommend item evoking same emotion, or let's say opposite emotion or similar emotion. Why were we able to do this? Because in the Plutchik wheel that you saw at the beginning, there are, in the Plutchik ontology that we developed, starting from there, there are also specifications about for example, which are the similar emotions. Similar emotions are the ones which are adjacent in the wheel, or the opposite emotions are the ones which are, let's say, on the other side of the representation. So, let's say, differently from standard recommender system, we were also able to suggest to a user to visit, for example, within a collection of the museums, item evoking opposite emotions with respect to the ones that he or she was watching during the for example, a visit or in a museum, or let's say items evoking similar emotions, okay? And this idea is important in the context of our project, because our project was aiming at providing an inclusive view, inclusive recommendation. So inclusive means that we don't do what the classical recommender system do. That means just to provide to the users the very same type of recommendation based on their preferences. So we try to extend a little bit the kind, so to break the bubble of our echo chambers, actually, by suggesting also, let's say, via this affective lens, items that are beyond our actual preferences, okay? So, and as I mentioned, let's say, this is the main novelty of the this second version of the system. The system was accessed via a mobile app. So we had people, in particular deaf people, were involved in this experimentation using this this app. They were able to go into the museums, scan, for example, the image of a painting, and were able to tag their feeling, so their memories about, for example, a particular kind of artwork. Their user-generated content is analyzed by the Gary system, and the system provides an initial explainable affective, let's say, label, and start to suggest to the users other items within the museums that are based on this kind of tripartite recommendation model. So same emotion, items with evoking same emotion, evoking similar emotion, or evoking, let's say, opposite emotion. We started to have an evaluation with deaf people, with 54 deaf people. 54 deaf people is a huge number for this kind of task, because usually, let's say, in the case of experiments, you have to have a professional translator in sign language to, let's say, explain the entire thing to them. And we used a 0.9 scale to, let's say, evaluate how much they liked the recommended the emotion-based recommendation of artistic items. And we can see here that yeah, there are two data here. The first one is that there is a certain resistance with respect to, let's say, a cognitive resistance with respect to visit or to, let's say, accept recommendation based on opposite emotion. Of course, okay, this is something that goes, let's say, somehow against what are our original preferences, but still it could be, let's say, useful in the area of let's say, museum exhibition, to explore also part or collection of a museums which, let's say, show, for example, the counterpart of the things that we have already, let's say, shown, we have already liked in the previous part of the visit. And let's say the items that received better ratings were the ones based on the suggestion of items recommended based on similar emotion. So emotions which are adjacent with respect to the Plutchik wheel. We also did an experiment about the explanation. So we asked to the people whether they were happy or not about the explanation provided by our system about why a given item was assigned based on their input to a particular category. And also here we let's say there was still a 0.09 scale. We have a median answer of 6, a mean of 5.81. Remember that let's say also in this case we were dealing with deaf people. So this was a particular subgroup that we investigated. And so on the scale of 0.9, this is, let's say, a sort of acceptable kind of rating. But we also did something more. We did a focus group with a professional sign language translator, asking to the actual target group of our work, to the deaf community, what were the elements missing in the explanation, and they gave us a lot of insights. So the first things that they told us was that they suggested to, let's say, provide not just a one-word explanation, which was what our system was able to provide. So it was able to say the system has associated the label love to this item because, for example, you have in the comments that you have used during your visit, you have used this word, okay, which is associated to that concept. But the idea is that their idea was that one of trying to provide a sort of snippet, so a sort of a larger semantic network that was, let's say, better able to explain this kind of association. Another, let's say, suggestion was that one of trying to, let's say, associate to the words some kind of visual representation, but here there has been a lot of sort of debate between the group of the deaf people, because within the Italian deaf community also it is not, let's say, first there are different level of let's say of knowledge of the language of the sign language. Second, a visual representation also provided as an image can have different interpretation by different people. So one of the solution could be that one of using short clips with the signed version of the word, because they also have problems in actually reading the actual words, and also actually problems in writing, in providing some comments during the visit. So these are, let's say, two main results coming out from this research. We have shown how this TCL common sense reasoning framework has been applied in the context of emotion-based content aggregation, because it is able to, let's say, aggregate all the items and all the kind of comments based on the items during a visit by using this kind of Plutchik wheel. And also we have started to test how, let's say, the perceived level of explainability for the deaf community of this kind of recommendation that our system provide, and let's say how much let's say they like these forms of inclusive recommendation. So recommendation that try to break the filter bubble of our own preferences to, let's say, open up a little bit our mind in order to see also things which, for example, do not perfectly fit with our own preferences. And so with the focus group, we had also some lessons learned, which are the ones that I was mentioning about how to improve the explanation. And that's it on my side, and I'm open to take questions.
All right. Can you hear me?
Yes.
Antonio, I have one question. I actually very much doubt that complex emotions can be explained as simple combinations of primary emotions. If this would be the case, then human life would be very simple, I guess. Just by making a fuzzy distribution on your Plutchik map, you do not make an emotion complex.
The point is that, okay, you are probably correct that this is a simple model. We used this model because it fitted very well with the kind of things that we can do with our compositional, let's say, reasoning framework. But we also tested our model with respect to let's say, other systems doing sentiment analysis or emotion extractions, which are on the market. And we actually saw that when we compared our system with the models which are on the market, our system were actually more nuanced. So we were able to cover, let's say, a huge part of this emotional spectrum. Why? Because this model, even if it is, let's say, probably a simplified version of, let's say, our emotional model, still is much richer than, for example, other models like the Ekman model, which is the one which is the most used in computer vision applications, which just has that 8 basic, let's say, emotions. So this means that, and also in the context of sentiment analysis, there are other models that are used that are only able to target, let's say, from 6 to 8 main basic emotions. While in this case, so we compared on our dataset, which is a museum dataset, the results of our system also with SentiNet, which is a very well-known, let's say, system also doing emotion extraction and sentiment analysis. So, for example, in that case, we saw that SentiNet has a better coverage on the basic emotions, but for what concerned the nuance, so the type of emotions which are extracted, our system does much better. So we were able to cover up of, I don't know, something like 32 emotions, which are out of, I don't know, 40 something, which are on the Plutchik wheel with respect to 14 in our data set. So it means that we really may have also in this simplified way a much more nuanced, effective classification. And SentiNet is a state-of-the-art model, okay, so for emotion extraction and sentiment analysis. So yeah, I probably agree with you that even the Plutchik theory is a simplified version of the problem. But I mean, from what, at least from what we saw in this project, this model was at least enabled us to have a more nuanced classification with respect to other kind of models.
I see. So you made some progress. Well, thank you.
You're welcome. Thank you, Alexei.
Thank you. Unfortunately, we don't have more time for questions. So congratulations, Antonio, and thank you very much for your presentation.
Thank you very much. Thank you.
Thank you. Well, now we will start with the presentation. Wait a minute. From
Hi, my name is Chalian for paper.
Sí, yes.
Okay, 97.
Yes, sorry.
No problem.
So has Chilan with a presentation entitled Cyber Neuro RT real-time neuromorphic cybersecurity. Please,
Okay.
Sheila, you can start your presentation, please.
Okay, thank you so much, and I apologize for getting the rooms mixed up. Can you see? Let's see. Can you? Let's see. You're seeing my display presenter view, and now you're hopefully just seeing the slides. Okay. So this is called CyberNeuro-RT, Real-Time Neuromorphic Cybersecurity, joint work with Weiler Zam, Tyler Stern, Malavam Bal, Professor Sengupta, Ashwin Jose, myself, and Srinivasan. Most of us are with Quantum Ventura, but Malaban and Professor Sengupta are with Penn State University. And so the problem statement is cybersecurity in HPC clusters, high performance computing clusters. So HPC clusters operate much faster and with much more data than you might find in typical IT domains that companies face. So how do we address this larger scale? So the tools that were created for traditional IT domains don't support this much, the greater amount of data and the faster throughput of this data. So neural networks is one way of doing it. And then in particular, you might use some edge-based hardware resident technologies such as neuromorphic processors to monitor and even predict events in HPC environments. So we sought to evaluate the viability of real-time HPC scale neuromorphic cybersecurity, and we call our system CyberNeuro-RT. So first we'll start with some data to simulate the high throughput environment. Data was adapted from the University of New South Wales dataset, includes many data sources like IoT, Windows, and Linux data. And then there's an feature extraction, early feature extraction called Zeek logs, which sort of monitor the packets. And with that, we had about 450,000 entries. 66% of this data was normal, and there was 9 attack types. So for the feature selection, so it started with originally 45 features. Then we removed 2, which were the label, having to do with the label, the type of attack. That was about 42 or 43 features, and then that's still a lot of features. So then we used a random forest classifier to down select among the original features. And then you'll see the results there on the right. It was picking things like source IP, destination IP, the bytes, the ports, the duration, service code, and things like this. And then this was used as an input into an autoencoder, and the autoencoder is doing a dimensionality reduction and looking for lower dimensional subspace, which explains normal versus abnormal traffic. We've continued this work and are looking at other ways of doing feature extraction and dimensionality reduction. So we used 85% of our data for training and 15% used for testing. And now I'll talk about the deep learning network that sits on top of the feature extraction methods. So we used a 10-layer deep neural network, 9 layers plus the 1 input layer. And we did some initial hyperparameter tuning using Keras Tuner. And that gave pretty good results, but we also wanted to explore the sort of edge computing ability of using neuromorphic computers. So within the neuromorphic computing market, there's 2 major offerings, Intel and BrainChip, with very different personalities, but we wanted to explore both. So what you see, you sort of have to translate from a full precision GPU model to a reduced precision neuromorphic computing model. And what you see in the right is the translation of the original artificial neural network down to a spiking neural network. So what happens is you remove things that are only used during dropout, only used during training, such as dropout, removing batch normalizations to the preceding layer, and then you convert, then you have a model which is compatible with the hardware, but has fewer features than the full precision GPU model. After that, there's some additional parameters one can tune on the spiking neural network. Things like how long do you run the integration time on the neurons, and other hyperparameters just having to do with simulating the artificial neural network with spiking hardware. So we had access to the Intel Loihi chip via the INRC Cloud Intel Neuromorphic Research Consortium. And then for BrainChip, we simulated their chips on CPU via a hardware abstraction layer. We now have access to both Intel and BrainChip's hardware, and we're doing continuing our experiments there. For Intel, we use the SNN toolbox to do the conversion, and for BrainChip, we used their product, which is called CNN to SNN. The process is similar to Intel in that you remove features that are not supported by the hardware, certain activation and layer types, and dropping things like batch normalization. And we also looked at something called design space exploration. So as I mentioned in the Intel case, there's a hyperparameter of how many time steps do you integrate the differential equations to simulate the neurons. So that's known as the threshold. And so we can vary that threshold to see how that affects the speed accuracy trade-off. More time steps means more accuracy, but also more time. So that speaks to the runtime control. There's also design time control, where you can have two different neuron types. In this case, we looked at the reset, integrate, and fire model and the subtractive integrate and fire model. Okay, here are our results. Using the full precision model, we got about 94% correct. Chance performance is 66%. And it was extremely fast, 0.34 seconds to do about 10,000 records. For the Intel, we also varied the precision of the converted model. At 8 bits, we got the same accuracy, 94%. At 4 bits, we got 67%, which is pretty much chance. For the BrainChip, accuracy also increased with precision, but were slightly lower. BrainChip got 83% at 8 bits and 67%, again, chance at 4 bits. Our work is one of the few and first papers that compare Intel and BrainChip on the same data set. Going forward, we will tune the BrainChip model to increase its accuracy and also try things on hardware, not just CPU simulation. With regards to the design time control, the subtractive integrated and fire was chosen over the reset integrated and fire model because it had greater accuracy. You'll see in the plot on the right there, where the blue is the subtractive integrate and fire, and regardless of the number of time steps that you run that model, it's always giving better results than the red line, which is below it, the reset integrate and fire model. So with that, I'd like to give a discussion and conclusion. The feasibility of real-time HPC scale neuromorphic cybersecurity was assessed. We call our system CyberNeuro-RT. We used algorithms including full precision deep learning and then conversion of deep learning to reduce precision spiking neural networks, and also design exploration within spiking neural networks. Neuromorphic implementations of the full precision networks were roughly comparable in terms of accuracy, but are much smaller and costly. So, for example, a GPU is the size of a GPU, but these neuromorphic computers are estimated to be about the size of a USB thumb drive. A GPU may be thousands of US dollars, whereas a neuromorphic computer is expected to be on the order of 50 US dollars. So this approach has been validated, and we're doing more research to prove this out. So there's a number of ways we can continue exploring this research, like tuning the networks to reduce false positives, trying the algorithms on hardware, using larger different data sets. One point to note is that in addition to using neuromorphic computing, we can also run the models on GPUs if a site prefers to do it that way rather than using neuromorphic computers. One thing we did learn is that there's differences between software simulation of the brain chip and hardware running of the Intel, and we intend to study these further. And for design space exploration, there were both design time control knobs and runtime control knobs. So with that, I'd like to conclude and thank the Department of Energy for this, funding this research. And we're now continuing this research in a phase 2. Thank you. I'd love to take questions.
Thank you. Yes. Thank you, Suhas. We have a few minutes, or are there any questions for the audience? It seems no. Okay. Congratulations, Suhas, and thank you very much for the presentation.
Thank you.
And finally, thanks to everyone here for your attention. This session has ended. Hi, Francisco.
Okay. We will have a break for lunch, and after that, the rest of the session will be in auditory. Thank you, everyone.
Thank you.